Jnanam paramam dheyam. Knowledge is supreme.
Right. So, let us begin with today's topic. So, this is going to be abstraction of linear algebra. So, the concepts that we have studied, namely Rn and so on, they are going to be made abstract now. The reason being, these concepts are used in other branches of mathematics as well as other branches in engineering and sciences. So, let us begin with the structure called vector space. So, the prototype for a vector space is Rn. So, where there are vectors, you can add vectors, you can scalar multiply vectors with various properties. So, a vector space V is a non-empty set and will denote by F the real numbers or the complex numbers. So, the set on the set V there are two algebraic operations defined. One is called addition. So, for a element A and B, so if we look at V cross V, so an element in V cross V is an ordered pair. So, A B that goes to an element in V which is denoted by A plus B. So, this is a binary operation of addition defined on the set V. And there is a operation called scalar multiplication, which is a function from the underlying field F, which is R or C cross V to V. So, given a scalar and given a vector, we will call it as a vector alpha comma A, it gives you something called the product alpha comma A, lambda comma A. So, these are two operations defined on vector space. One is addition, other is we call it as scalar multiplication with the usual properties that the vectors in R3, R4, Rn have. Addition is commutative, it is associative. There exists a unique element 0 in V, a 0 vector such that A plus 0 is A, and that is same as 0 plus A because of commutativity. And for every A, there exists a negative of A, such that A plus minus A is equal to 0. And scalar multiplication distributes over addition. So, lambda scalar multiplied A plus B is same as lambda A plus lambda B. And similarly, if you add two scalars and multiply with A, then it is lambda A plus mu of A. So, this is regarding addition, and here is there is a multiplication of scalars. So, that says lambda multiplied with mu of A is same as lambda mu multiplied first and multiplied with A. So, normal properties that we know of scalar multiplication in R3. So, these are made as properties, defining properties of scalar multiplication on a abstract vector space. And finally, 1 times A, the scalar 1 in the field is equal to A. So, that is a normalization one calls. We have said in the here that these are the unique 0 and minus A, but those can be proved using the properties. So, and one can also prove obvious facts that 0 times A is 0 is lambda times 0 and minus 1 multiplied by A. So, this is a additive inverse in the field, and that is same as minus of A. So, these are some obvious properties that one can prove using those axioms itself. So, we will not prove that, we will just assume because we do not have that much time, but it is a nice thing to deduce these properties from the basic axioms of addition and distributive properties. Right. So, let us look at some examples of vector spaces. Rn and Cn are the prototypes of vector spaces. So, you can take vectors Rn, that is n components, right. So, two vectors you can add them component wise, and scalar multiple is multiplying each component by that scalar, and similarly Cn. So, Rn is a vector space over the reals. Cn can be treated as a vector space over reals as well as a vector space over complexes. So, the underlying scalars you can choose whichever you like. So, they will give you two different objects, one will be Cn as a vector space over R and other will be a Cn as a vector space over the complex numbers itself. This also we had studied that look at the null space of a matrix A. So, given a matrix, look at the null space, that is Ax is equal to 0, all solutions, we saw that that forms a subspace of Rn, we call that as a subspace. So, which is a vector space in itself. You can also look at all matrices M cross N, real matrices or complex matrices. So, that is a set V. You can add two matrices, right. You can take a scalar multiple of a matrix and it will have all those properties that we have been actually using them. So, that this is a vector space, all M cross N matrices form a vector space over the field of real numbers and complex numbers, right, all M cross N with complex entries. Again, this can be treated as a vector space over R or over C, both are possible. Let us look at something which you might not have come across. We will look at all polynomials of degree less than or equal to 3. So, look at all polynomials of degree less than or equal to 3 with coefficients being real coefficients, right. So, what does it look like? It is an expression of the form a0 plus a1x plus a2x square plus a3x cube, right, where x is a variable, right, where a0, a1, a3 are scalars, real scalars. You can also think of complex polynomials over the complex numbers, where the coefficients are complex numbers. Why this forms a vector space? Given two polynomials, right, of degree less than or equal to 3, you can add them. You will again get a polynomial of degree less than or equal to 3. You can multiply a polynomial by a scalar. So, only the coefficients of the powers will change, right, but the degree will still remain less than or equal to 3, and it has all those properties that of commutativity, associativity and so on. So, these are no, you can have anything. So, that is the next thing. You see this, you can have R d, polynomial of degree less than or equal to any number d, right. So, there all will be different vector spaces, examples are different, right. The constant polynomial, that is the real numbers itself, right. R1 is the real number itself, you can have R2 x, right, all linear polynomials, all quadratic, all cubic, right, and so on. So, there all are different vector spaces. Okay. You can also think of all polynomials, all real polynomials, whatever may be the degree, put them all together in a box. So, what is this R x? It is nothing but the union of R n x, where n goes from 1 to infinity. Take any polynomial or any degree, so that is an element of R n. So, how do you add them? How do you add a cubic and a polynomial of degree 5? You can treat cubic also as a polynomial, but not of degree 5. It is a polynomial of degree 3 only, but the coefficient a4 and a5 are 0, right. So, you can treat as a polynomial, right, with x5 coming, but then you can add them. So, basically the idea is given any two polynomials of any degree, different degree, you can add them by adding coefficients of like powers, right. That was what we have been doing all along actually, right. So, that addition becomes commutative, associative and so on. So, that is a space of all real polynomials, or you can also have complex polynomials and the coefficients are complex numbers. So, these are examples. This is something that you will come across in your differential equations course. Look at the solutions of the differential equation y double dash plus y square y equal to 0, or y dash plus qx plus y equal to 0. Look at, so what do you mean the solutions of this equation? You are looking at a function y which satisfy the properties double derivative plus y square y is equal to 0, right. If you have two solutions y1 and y2, and if we add them, that will again be a solution of the same equation, right. If y1 satisfies this, y2 satisfies this, y1 plus y2 also will satisfy the same equation. So, addition is defined, scalar multiple again will define, it is like something like homogeneous, right side is 0. So, that is not going to change, right. So, this is normally this one calls the homogeneous differential equation, but we will study these things in differential equations or solutions of this type. So, this is a second degree differential equation, this is what is called a first degree differential equation. So, if you have already done a course in differential equations, you might have already come across, if not, when you do it you will come across these things. You can also look at this in the vector form. So, this is a vector, that means it is y1t and y2t, these are the two components of this, and you can have satisfying the equation y dot dot. What is y dot dot? So, that is equal to the second derivative of y1 and second derivative of y2. So, that is notation for that is equal to ay. So, solutions of this also will form a vector space. So, that is one of the reasons why these vector spaces are important, abstract vector spaces, because they find applications in study of differential equations. So, these are some of the examples. So, let us go a step further. What did we do in when we had subspaces of Rn? We started looking at, given a subset of vectors, we started looking at linear combinations of them, we started looking at generating a subspace with them, then started looking at when is a minimal set of generators, right, we call that as a basis and so on. So, same things are possible here in abstract vector spaces also, but before that let us just look at if we look at all real matrices with entry bigger than or equal to 0, does this form a vector space under addition of matrices? Look at all real matrices m cross n, okay, such that all the entries are bigger than or equal to 0. Do you think this forms a vector space? Of course, if we add, you will get again a matrix of the same type, but if you multiply by a scalar, you may not all get a matrix of the same type, because if scalar is a -1, if all entries are positive, when you multiply by -1, you get all entries negative, right. So, that will not be an element. So, scalar multiplication, the usual scalar multiplication does not work, maybe some other scalar multiplication you can define. So, that says that in a for a vector space, it is a set which is important. It is important also what is the operation of addition defined on it, what is the operation of scalar multiplication defined on it, right. It should have all those properties, and whether it is over real numbers or it is over complex. So, you can think it as 4 things in a vector space: a set, addition, scalar multiplication and the underlying scalars. All these 4 put together characterize a vector space. If any one of these changes, then you get a different example of a vector space. Okay. For example, look at solutions of this x y dash plus y equal to 3 x square. If I take y1 and y2 to be solutions of this differential equation, that means what? That means x y1 dash plus y1 is equal to 3 x square, and y2 is another solution. So, x y2 dash plus y2 is equal to, so can I say y1 plus y2 also satisfies this? Because if I put y1 and y2, of course, this will give you 2 derivatives, this will give you y1 plus y2, but right hand side you will get, you will not get 3 x square. When you add those two equations, you will get 6 x square, right. So, it was only when it was 0, it became a right vector space. So, this is not. So, the usual addition of functions and scalar multiplication will not give this as a vector space, right. Similarly, of y dash plus y square. So, these are something which are non-linear. So, this is non-homogeneous because right hand side is not 0, and here it is y square coming. So, it is non-linear part coming, right. So, that is why it will not give a subspace. So, study of non-linear differential equation and non-homogeneous differential equation will be a part of your course on differential equations, right. So, let us define the concept of a subspace. Given a vector space and given a subset, right, we can think of treating subset itself as a vector space, but that is possible only when given two elements of the subspace you add, you again get an element of that subset, right, and scalar multiple also should be part of it. So, a subset is called a subspace if given two elements W1 and W2 and two scalars. If you take a linear combination of that, that should be again inside the same set, right. So, that means a subset which is closed under linear operations of addition and scalar multiplication can be treated as a vector space in its own right. So, we call that as a subspace, right, with the same addition and scalar multiplication taken from the original one. Okay. So, for example, so let us look at all polynomials. We had a vector space of all polynomials. Look at polynomials of degree less than or equal to 5, that is a subset of the space of all polynomials. And if I take any two polynomials of degree less than or equal to 5 and add, I again get a polynomial of degree less than or equal to 5. A scalar multiple again has the same property. If it is a polynomial of degree less than or equal to 5, scalar multiple again is. So, you can treat polynomials of degree less than or equal to 5 as a subspace of the vector space of all polynomials. So, each polynomial of any degree, say less than or equal to n, right, can be treated as a subspace of all polynomials. Quadratics can be thought of, right, as polynomials of degree less than or equal to 2 as a subspace of cubics, polynomial less than or equal to 3, right, that is also possible. So, all these are subspaces. So, now question is how do we define describe a vector space. So, let us look at what is called linear combinations. So, once addition is there, scalar multiplication is there, given elements V 1, V 2, V k and given scalars C 1, C 2, C k, you can form this new element, right. So, this is called a linear combination of the vectors V 1, V 2, V k. Keep in your mind the prototype of R n, something similar happening, but we are not saying that this V is R n or C n or anything, this is just abstract. For example, you can take polynomials, V 1 could be a quadratic, V 2 could be a cubic and so on, you can add them, you will again get a polynomial, right. So, given elements of a vector space, you can form and scalars, you can form a linear combination of that. So, that is this element. And you can now put together all the linear combinations in a box and you will call that as the span of that set, right. Like, so, given a set S, subset S of V, look at all sigma alpha I V I, where this n could be any number, could be taking 3, 4, n, and choose any finite number of V 1, V 2, V n in S, take same number of scalars in F and form that linear combination. So, what is this called? So, this will be a finite linear combination, right. This is a linear combination and we are defining only finite linear, because if it is infinite we do not know how to add them anyway. In a vector space you cannot, there is no concept of adding infinite number of them, right, only finite number is possible, because you can add again and again till a finite state. So, look at all linear combinations of elements of S, okay, where n is varying, alpha i's are varying and v i's are varying. So, all possible linear combinations, call that as the square bracket S. One can show easily that if you take two linear combinations, then sum is again a linear combination, scalar multiplication is again a linear combination. So, this is a subspace and this is called the subspace generated by S, right. So, given a set S in a vector space, what is the subspace generated by it? Is a set of all possible finite linear combinations of elements of S, right, that is called the subspace generated. So, here comes if S itself is a finite set, say that the space generated by S is V, we say it is a finitely generated vector space. If V is a vector space and we have got a finite subset of it, say that when I take linear combinations of elements of that finite set, that gives me everything in V, right. Every vector in V can be obtained as a linear combination of elements of that set S, and if that S is finite, we say our vector space V is finitely generated, right. Finite number of elements of V give everything via linear combinations. If it is not, then we say it is non-finitely generated vector space. That is where abstract vector spaces will start differing from your R n and subspaces of R n. So, let us look at some examples of this. R n and C n, are they finitely generated? Yes, we know that standard basis is there 1 0 0 0 1 0, right. That is the standard basis for R n, similarly for C n. Null space, that is actually a subspace of R n. So, that is also finitely generated, and actually that became an important thing in our solving system of linear equations, how to find a basis for n of a. What is the dimension of n of a? We call that as a nullity, and finding a basis for n of a, right. That is a solution space of a homogeneous system. All matrices, do you think all matrices form a, is finitely generated? That means what? Every matrix M cross n can be obtained as a linear combination of some finite number of matrices. Let us look 2 by 2, for example, A, B, C, D, right. I can write this as, take the first element as A, all remaining 3 as 0. Next, B, all these 3 remaining elements 0. So, I can take 4 matrices where first, right, one element is the A, B, C or D, and remaining 3 are 0. If I add these 4 matrices, I get the matrix A, B, C, D, and A can be taken out. So, A times 1 0 0 0, B times 0 1 0 0, and similarly other 2. So, basically what we are saying is, if you look at a matrix M cross n, it is nothing but R to the power M cross n. Think it now. How many elements are there in a matrix of order M cross n? Is M times n, right. Instead of, only thing for convenience, we are adding first M elements as first row, right, second as second row, third row, fourth row, mth row, right. But if I write everything as a one string, first row, right, and then the next row, and then the next row, but written is only as one long string of elements. How many elements will be there? M cross n. So, I can identify a matrix of order M cross n with R to the power M cross n. And what is the basis for R to the power M cross n? Standard basis, 1 at one place and remaining all are 0. That is what we are saying. That is the basis for matrices also, essentially, right. And actually, it is not just for the sake of getting this basis. That is how a computer stores your entries of a matrix. Computer does not know what is a row, what is a column, right. A machine only knows a string of elements that you are giving to store. You say 5 as the first element. So, it has binary way of storing. So, it will store 5, next element, next element, next. When your one row is over, you have to give some command to say that now you are starting a new counting, right. That is possible in a computer. So, first n elements is first row, next n is second row, next n is third row, and so on. So, that is how a computer stores the data in it, right. So, that is the way we are saying we can find a basis for n matrices of order n cross n also.